So last time we started talking about aromatic systems. What does it mean for a system to be aromatic? No, those are the rules. What does it mean to be aromatic? No. What does it mean to be aromatic? Not the rules that contribute to it, but what does it mean to be aromatic?
More stable.
More stable. It's unusually stable, right? It's not what you would predict at all. In fact, we find that aromatic systems do kind of some odd chemistry. They don't do things that you might expect a normal carbon-carbon double bond to do, okay? Now, let's talk about the rules. We talked about there are 4 rules that must be satisfied in order for a system to be aromatic. You do not have to give them to me in order, but you need to give me all 4. What are they?
Cyclic.
Must be cyclic. Planar. Pardon? Just conjugated? Completely conjugated, right? I have many conjugated systems. So you have to have complete conjugation. And what's the last one? Huckel's rule, which is what? What's the equation? 4n plus 2 equals the number of pi electrons, right? All 4 of these things have to be satisfied in order for a system to be aromatic, right? And so I've got several systems up here right now. Let's go through them. Aromatic or non-aromatic? So this one's aromatic. Aromatic or non-aromatic? Aromatic or non-aromatic? It is. And how come? It's cyclic. It is planar. If you build a model of naphthalene, you'll find that it's planar. It is completely conjugated. Each atom has a p orbital on it, right? And it does satisfy 4n plus 2. How many pi electrons does this molecule have? 10. And that satisfies the rule when n is equal to 2, right? And so that satisfies Huckel's rule. N for Huckel's rule has to be 0, 1, 2, 3, 4, so on and so forth, right? It can't be a fraction. So that is an aromatic system. Does anybody know what naphthalene is useful for, or is used in? Mothballs. That's exactly right. So it's useful for more than that, but if you've ever worked with mothballs or whatever, your grandparents keep them in their closet, keep the moths out of their woolen stuff, right? That's what it is, the major component. How about this one? Why not? I've drawn it planar. It is fully conjugated. It's not. It's actually tub-shaped. That's right. Okay? But if you didn't know on an exam, it also doesn't satisfy one of the rules other than just planarity. Which one doesn't it satisfy? It doesn't satisfy Huckel's rule. In fact, it satisfies 4n equal 8, right? And that is the rule for anti-aromatic. So if this actually was planar, it would be anti-aromatic. And that's why it's not planar. It's actually tub-shaped to keep it from having this anti-aromatic character. So this would be an anti-aromatic if planar. Just to put a note there on that, right? So what do we expect for the chemistry then? Chemistry of this should be very similar to the chemistry of this, right? It's just going to do additions across the carbon-carbon double bonds. May do it more times than you might expect, so on and so forth. Okay? But that's the chemistry of aromatic systems. Those are the things that you need to know for the test that's coming up at the end of the week. Okay? So here we've got an example of 2 molecules. We got cyclobutadiene, 4 pi electrons. I think we finished off with this slide last time, right? It's anti-aromatic. It has been synthesized. It only lasted for a fleeting moment at frozen argon temperatures, basically, but it was detected. Didn't exist very long. And so we can account for the difference with these rules for aromaticity, but really this comes down to molecular orbitals. Okay? So if we have 6 p orbitals for a benzene ring, how many molecular orbitals should benzene have? 6. It should have 6 molecular orbitals, right? And, you know, to draw what they all look like can get kind of daunting, But it turns out that aromatic systems have this wonderful little thing, and it's called the frost circle, okay? Or the inscribed circle method, but I like to call it the frost circle. And it turns out that if you draw a regular polygon that you suspect might be aromatic, where one of the vertices is pointing straight down, your orbitals are taken care of for you, okay? So benzene, right, is a hexagon. So if I draw one of the vertices straight down, and if you inscribe a circle around this, everywhere the circle touches one of these vertices, that's where the energy level of an orbital is. So really you've got an orbital here, 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 and here. So you've got your 6 orbitals, right? So if I just draw that out again without the, you'd have something that kind of looked like this, okay? Those are the 6 orbitals. The orbitals that are on the same level, what do we call those? So I've got this, and then these 2 orbitals, right, are at the same energy. What do we call orbitals that are at the same energy? What? We call them degenerate. Okay? Kind of like your cousins. They're degenerates, right? They're degenerate orbitals. They're at the same energy. The only thing is that they're oriented at different arrangements in space, okay? But otherwise, they are equivalent. Now, if you take the midpoint of this orbital collection, you'd get a line that kind of goes through here. Half of them are above, half of them are below. Now, how do we start filling our electrons in the molecular orbitals? Where do we start? And how do we go? Now what do I do? Now what do I do? Have I taken care of all my electrons? Yes. And if you have all of those orbitals filled that are below that dotted line, it is an aromatic system. It's easy to get the molecular orbital energy diagram for a simple, single ring aromatic system. So something that's a regular polygon. So now if we were to do cyclobutadiene, a box with 2 alkenes in it, right? How would I do this? How would I do the frost circle for this one? What do I have to do? I have to turn it into a diamond, so one of the points is straight down, right? And I always have trouble drawing that one myself. Right? But if you look at that, then you've got an orbital, an orbital, an orbital, and an orbital. Where am I going to draw the dotted line? Right at the middle. And so how many electrons do I have to put in? 4. Anna. Can everybody tell me now why that is more reactive than you might expect for an alkene? It has 2 unpaired electrons. It is a diradical. What do we know about radicals? They like to react, right? No wonder this thing doesn't behave like a typical alkene. It reacts more reactive than a typical alkene because of how the electrons are populated in the orbitals, okay? There is almost always some type of frost circle question on this exam that's coming up. I love it, okay? You need to be able to know your energy diagrams for aromatic systems, and it's pretty easy to do with the frost circle, okay? So, all right, whatever we get through today on these slides is what we will be held accountable for the exam. So today we're going to continue to talk about aromatic systems. But we're going to talk about some heterocyclic aromatic compounds, that is, aromatic molecules that have heteroatoms in them. Not everything has to be a pure hydrocarbon. We'll talk a little bit about aromatic compounds in biochemistry and why it's important, okay, at least on a very thin level. And then hopefully we'll get to where we start talking about electrophilic aromatic substitution reactions, which is the chemistry that benzene and aromatic systems can undergo. They don't do addition chemistry. Okay, EAS, the A does not stand for addition. Okay, it's electrophilic aromatic substitution. So we can do substitutions on aromatic systems, and we'll see why that is. This is an example that we've already talked about, pyridine. Pyridine satisfies all of the 4 rules of aromaticity, right? It's cyclic, it's completely conjugated, it's planar, as you can see in the diagram, and it satisfies Huckel's rule, okay? It has only 6 pi electrons. In this case, the lone pair electrons do not count because they are orthogonal to the pi system. That lone pair of electrons is 90 degrees to the p orbitals. Those electrons cannot participate in conjugation with the aromatic ring, so we do not count them, okay? So there are only 6 pi electrons. That satisfies Huckel's rule. Everything is fine and dandy, and it is an aromatic system. Pyridine is pretty stable. It smells like rotten fish, okay? It's a base. Why is it a base? That pair of electrons right there, not being tied up in resonance, can do just normal base things. Okay, it can accept protons, and it can act as a nucleophile, and you can do all kinds of stuff with that pair of electrons. Okay, but it is an aromatic system. Okay, here we have an example of pyrrole. Pyrrole, we have to count the lone pair of electrons. Why do we count the lone pair of electrons here? They are in line because it's the hydrogen that is perpendicular to the pi system. Those lone pair of electrons are actually sitting in a p orbital that's in conjugation with all the other p orbitals. It's part of the pi system. So if I look at pyrrole, right, it is cyclic, it is completely conjugated, it is planar, and it satisfies Huckel's rule. 2, 3, 4, 5, 6. That is an aromatic molecule. Okay? Yes, sir? You need to build a model. So when you build the model, what you'll find is that the hydrogen atom is in the plane of everything else, and the lone pair of electrons from your model, that little stick, will be actually sticking up in the pi system. So you'll be able to see it. Okay? If we look at systems like the so-called cycloheptatrienyl hydrocarbon, these molecules are actually interesting in that the hydrogen here doesn't get lost as a proton, but it gets lost as an H-. It gets lost as a hydride. So it turns out that this molecule is actually a pretty decent H- donor, and it can be used in chemistry in similar situations to sodium borohydride. It's not as strong a reducing agent as sodium borohydride, but it kind of can do some of the same stuff. The reason it likes to give away a hydride, one of these hydrogens is H-, the hydrogen with its pair of electrons, okay, is because if we form the so-called tropylium cation, okay, what you'll notice is it all of a sudden becomes aromatic, right? It's planar, it's completely conjugated, it's cyclic, and it satisfies Huckel's rule with 6 pi electrons. And so molecules like this will lose their hydride very, very easily and form these stable so-called tropylium ions. And if you take a higher level chemistry course that involves spectroscopy, like mass spectroscopy or things like that, this is one of the reaction mechanisms that happens quite frequently in those spectroscopy experiments. You see the tropylium cation, and it has to do with the fact that it generates this aromatic system, okay? And so you can actually take the polygon, you can turn it upside down where one of the points is facing straight down, you can see all of the orbitals that you have to deal with, And when you populate them, you see that the below the line is completely filled. And so it satisfies all of the rules for aromaticity. What if we tried to use this as an acid where it lost a proton? What would the situation be? If it lost H+, would it be aromatic, anti-aromatic, or non-aromatic? It would be anti-aromatic. It would satisfy 4n equal the number of pi electrons. And why on the orbital diagram would it appear to be so reactive? So how many electrons would we be putting into the system if it lost a proton? 2, right? And where would those 2 electrons go? One would go here, and one would go there. And again, we would have this diradical species that would be extremely reactive, okay? And so the same energy diagram, but we can, depending on how many electrons you put in there, determines whether or not you're dealing with an aromatic, non-aromatic, or an anti-aromatic system, okay? Cyclopentadiene likes to lose a proton. And in fact, if you think about this, cyclopentadiene has a pK of about 16. What else do we know has a pK of about 16? Alcohols do, right? What other types of reagents do we know of that have a pK of around 16? Alcohol is a functional group, and that's true, but what kind of reagents might we use that have a pK of around 16? Water's close. What's the conjugate base of water? Hydroxide, right? I can take cyclopentadiene and I can treat it with sodium hydroxide and I can remove this proton. And it's nothing more than a pure hydrocarbon. I can take sodium hydroxide and mix it with hexane, nothing happens. I can take sodium hydroxide and mix it with this, nothing happens. But I mix it with cyclopentadiene, it reacts and it generates the cyclopentadienyl anion, okay? And it turns out that that anion is aromatic. That's why this proton is so acidic, because if it loses it, it gains that aromatic stability, and that lowers the energy of the system. So some hydrocarbons, if they can gain aromaticity by either losing a hydride or losing a proton, they will. They will do that, and they will become aromatic anions. Okay? Now, if you look at the cycloheptatrienyl, the pK of this is 36. I can draw just as many, I can actually draw more resonance structures for this anion than I can for this anion. But it's still got a much higher, that's 20 orders of magnitude. That's a huge difference. Yes, I can draw more resonance structures, but none of these resonance structures are aromatic. In fact, if it was planar, what would it be? If these molecules were actually planar, would they be aromatic, non-aromatic, or anti-aromatic? They would be anti-aromatic. This does happen. I can get a base that's higher than 36, but these anions must be what? What's their structure? I can treat this with something like butyl lithium, which is a very strong base, and I can generate these anions. But what would their shape be? Would they be planar? They would not be planar. They would actually be puckered. If they became planar, you would have an anti-aromatic system. So they bend, and they do not form aromatic or anti-aromatic structures. They are not planar at all. All right, so now I think we've got a pretty good handle on what aromatic systems are. You know the 4 rules, right? You should be able to apply them to a variety of systems and come up with a good guess anyway of which systems are aromatic, anti-aromatic, or non-aromatic. You will find a lot of aromatic compounds in biochemistry. Amino acids contain aromatic systems. This is phenylalanine. It's an essential amino acid. You've got to have this in your diet, okay? Phenylalanine has an aromatic ring in its side chain, a benzene ring. Benzene itself is carcinogenic. You put this other stuff on it, and now all of a sudden we have to have it in our diet. You have no mechanism in your physiology to synthesize phenylalanine from other precursors. You have to have it. Tryptophan is another essential amino acid. It too is an aromatic ring. Looks like we got two rings there, right? But it's one aromatic system. How does this satisfy the rules of aromaticity? Okay, each atom has p orbitals, right? So it's completely conjugated. It is cyclic. It is planar. And it does satisfy Huckel's rule. How many pi electrons do we have? We have 10. 2, 4, 6, 8, and 10. We have to count the lone pair on nitrogen. Okay?
You always count the lone pair?
Not always. Not in pyridine. Depends on the shape. If the nitrogen has a hydrogen attached to it, that lone pair has to be in the plane. Okay? Tryptophan. What do y'all know about tryptophan? You probably know something that ain't really true. You've probably heard that it makes you sleepy, and that it's in these sleep pills, right? And they probably do. But all they're doing is getting you to buy an essential amino acid for nothing and won't make you sleep. Mm-hmm. Okay? You probably heard that, oh, you eat turkey, turkey's high in tryptophan, and you go to sleep, right? That's more nonsense, right? It turns out that if tryptophan actually made you sleepy, you would be better off eating cheese, because cheese has more tryptophan in it per ounce than does turkey. Okay? I've never heard anybody tell me they ate cheese and went to sleep. Why is it that the turkey myth exists? Anybody know? Because you eat so much. It's Thanksgiving Day. You go in and you sit down in a comfy chair, you turn on the football game, and you fall asleep. You get comfortable. It's not because you ate a bunch of turkey. Okay? There are other biological system or biological molecules that contain aromatic rings. Purines and the pyrimidines, these are heteroaromatic systems that are in DNA and RNA. These are part of your base pairs, right? Why is it so important that we use aromatic systems in DNA? Stability. That's exactly right. You can go out to an archaeological dig site, find some preserved tissue these days that may be 1 million years old, and actually get usable DNA that you can actually extract and sequence. They do it all the time. The reason that that's possible is because DNA is built upon these extremely stable systems, these things that are aromatic. Okay? So which of these lone pairs of electrons do we count in the aromatic system, and which of those lone pairs in purine do we not count in the aromatic system? So let's start. Do we count or not count? Count or not count? Count or not count? Yeah, we count those. Count or not count? All right, good. So anytime the nitrogen has a hydrogen on it, you are going to count, and if they don't, you won't, right? So let's do a quick little quiz here. Using the frost circle method, predict which of the following species is aromatic, non-aromatic, or anti-aromatic. I'm going to throw a third one in there. So draw the frost circle for all of those. Two of them will actually have the same frost circle. One of them I've got on the board for you. All right, so how about the first one? Aromatic, non-aromatic, or anti-aromatic? Anti-aromatic. We're assuming everything is planar here. How about the second one? Aromatic or anti-aromatic or non-aromatic? It is aromatic. Why is it aromatic? It satisfies Huckel's rule, but that in itself doesn't. How does it satisfy Huckel's rule? 4n plus 2 equal the number of pi electrons. How many pi electrons do I have here?
2.
So what must n be? And that works, doesn't it? How do I know it's planar? 3 points always define a plane, going back to basic trig, right? 3 points always define a plane. I cannot have non-planar cyclopropane anything. Those 3 carbon atoms must lie in the same plane. It is a mathematical law, right, that 3 points define a plane. So we have an aromatic system. And in fact, this is the simplest aromatic system you can draw with 2 pi electrons, which is the bonus thing that you were supposed to come up with for today, right? It's the easiest way to come up with an aromatic system with 2 pi electrons. How about the cyclopropynyl anion? That would be anti-aromatic. And again, this probably can't even exist very easily, right? It would probably have a very short lifespan because it can't tort and distort itself out of planarity. Again, because 3 points define a plane. It has to be planar. Okay, it's not like cyclobutadiene. Actually, cyclobutadiene, when it forms, if it were to form, would actually pucker up a little bit like an envelope. And the cyclopentadiene anion, it is aromatic. Has 6 pi electrons, it's planar, completely conjugated, and it is cyclic, obviously. Okay? So, I told you I'd have a demonstration for you this morning. And so I've got safety equipment here. And if benzene were really just a bunch of alkenes, we would expect that we could add halogen across the carbon-carbon double bond. Right? We can do that all the time. And so the halogen that I'm going to pick on today is bromine. Because it's a liquid, I can handle it pretty easily. So this is a solution of bromine. Okay, I don't know, it's got just a couple of drops of bromine in there, and most of it's dichloromethane. Okay, but I think you all will agree that's a nice, easy to detect color, right? Kind of reddish brown. And if we were to add this to an alkene, what would we expect to happen? It would go clear. We would be adding the bromine across the carbon-carbon double bond. Well, I happen to have a solution here of cyclohexene, which is the one that we have drawn up there with the X above it, right? We said that that was not aromatic, right? So when I add a few drops of bromine to this, what should the observation be? The observation should be, right, that it goes clear. So I'm going to take a little bit of bromine solution here. Hopefully not get it on myself. And what you'll see is maybe if I hold it a little bit. As I'm adding it in, you can see the color dissipates quite rapidly. Right? So we have just done the addition of bromine across the carbon-carbon double bond. Now, I've got a solution of benzene. I'm just going to take a small amount. And what you recognize, right, is that the color persists. It's dilute, but the color persists. And I'm getting a lung full of bromine up here. Whew. But it doesn't do the chemistry that we would expect it to do if it were just a bunch of alkenes, right? It doesn't do addition chemistry. But it does do chemistry. We can do chemistry with it. You all are going to do some electrophilic aromatic substitutions in lab this semester. And so what we're going to do is react this with an electrophile and actually replace the hydrogen with that electrophile. So if the electrophile happens to be a carbon atom, we can generate new carbon-carbon bonds, but quite frequently the electrophile will be something else, like a heteroatom, like chlorine or bromine, or nitrogen, okay? There are a lot of reactions that you're going to have to learn that are electrophilic aromatic substitution reactions. That's the hard part. The easy part is the mechanism is essentially the same for all of them. As long as you know how to get the electrophile, the mechanism itself is the same, okay? And we have what's called the general electrophilic aromatic substitution reaction, which is the mechanism, okay? So let's look at some examples. So if I take an aromatic ring, in all of these cases I'm just going to pick on benzene, and I react it with chlorine or bromine, so that's X2, in the presence of iron trichloride or iron tribromide, we need a catalyst, I can replace the hydrogen with a halogen. It doesn't do an addition, it does a substitution. Why does it do substitution and not addition? Okay? Okay, yeah. If you look at the starting material, it's aromatic. What's the product? It's aromatic. If we did addition across the carbon-carbon double bond, would the product be aromatic? No, it would just be a conjugated diene. It would lose that stability that we get from aromatic systems. And so that's why it likes to do these electrophilic aromatic substitutions. Now, in the box, the electrophile, they put as Cl plus or Br plus. I put those in air quotes. You will not really have bromine plus floating around in solution. You will not really have chlorine plus floating around in solution. But it will behave in the presence of that iron catalyst as if it were Br plus and Cl plus, okay? You can take an aromatic ring and you can use a mixture of nitric acid and sulfuric acid and you can put a nitro group on it and make nitrobenzene, okay? Very, very useful reaction. The electrophile is the nitronium ion, NO2+. The nitrogen bears a formal positive charge. This is useful to take an aromatic ring, put a nitro group on it. What can we do with the nitro group? Lots of things. We can add more nitro groups and have an explosive, for example. Trinitrotoluene is a toluene ring with 3 nitro groups on it. It likes to go boom. This is how they made it back in the day. You didn't start with benzene, you started with toluene. You mixed it all together, you used sophomore level organic chemistry, and you just prayed you didn't die doing it. Okay? It's very sensitive. Putting 1 nitro group on is easy. 2 nitro groups, 3rd nitro group, be careful. It's going to go off on you. Okay? So you got to be careful about that. Sulfonation. If we use a mixture of sulfur trioxide and sulfuric acid, we can replace the hydrogen with the sulfonic acid group, in this case making benzene sulfonic acid. The electrophile has the positive charge on sulfur. This is useful for making detergents. Many detergents actually have sulfonate groups. So a lot of the detergents that you might use in your microbiology laboratories or in your cleaning things that you all use, whatever products, they frequently contain artificial soaps, which are called detergents. And many of those will contain sulfonic acid groups. Okay? I can take an aromatic ring and I can make carbon-carbon bonds, either a typical carbon-carbon bond like an alkyl benzene, or I can replace the hydrogen with a carbonyl, okay, and make things like ketones. Both of these bear a name, and you need to know these by name. These are Friedel-Crafts reactions. When I'm making a bond to an alkane, this is called Friedel-Crafts alkylation. And when I'm making a bond to a carbonyl, this is called Friedel-Crafts acylation. Okay? In both cases, it is a carbon atom that is the electrophile. So how do we generate that electrophile? Well, we typically use an alkyl chloride and aluminum trichloride to generate a carbocation, which is the electrophile. Aluminum trichloride pulls the chlorine off of the alkyl halide and generates a carbocation. Okay? What functional group is this? RC double bond OCl. It's one of the functional groups we talked about last semester. It is an acid chloride. Acid chlorides will also react with aluminum trichloride to generate what we call acylium ions. We'll talk about that more later, but it's a carbon with a positive charge on it, but it is not a typical carbocation because of the oxygen, okay? And you form these ketones. So, you just learned how to make carbon-halogen bonds. You just learned how to make carbon-nitrogen bonds. You just learned how to make carbon-sulfur bonds. And you just learned probably the last way that you're going to learn how to make carbon-carbon bonds. The last real way. There'll probably be some other reactions that we talk about, but they'll be involving this type of chemistry. Okay? You need to memorize these different reagents. What can you tell me about the halogen-forming reaction? What are we limited by? I'm limited to chlorine or bromine. I can't make carbon-iodine bonds through this chemistry. Iodine isn't that reactive. You have to have other chemistries to do it. What else is absent? Fluorine. Too reactive. Goes boom. Bit of a problem. Chlorination and bromination, very easy to do. Bromination is probably the easiest one on a laboratory scale because bromine's a liquid. I don't have to worry about gaseous chlorine. Okay? Here we yes, sir. You can, but we're not going to talk about that today. Okay? That's not going to be on the exam. But you can put more than one substituent. Then where that second substituent goes becomes an issue, and we'll have to learn that. But right now we're just talking about the general reaction. Okay?
And the examples that you're going to give, are there going to be any substituents off of the benzene, and how would that affect?
Not yet. We're not there yet. Okay? And it will affect. Just to kind of foreshadow a little bit. So you need to memorize this. If you want to put a halogen on, you need the halogen and iron tri-whatever halide. Okay? If you want to put a nitro group on, you need a mixture of nitric and sulfuric acid. If you want to put a sulfonic acid on, you need SO3 and H2SO4. If you want to make a carbon-carbon bond, you need to do some type of Friedel-Crafts chemistry. Okay? So let's talk about the general mechanism. And I like to keep this very, very simple. And we're just going to use electrophile, E+. Doesn't matter what it is. And let's use benzene, so I'll erase everything but benzene. So I know that if I have my benzene, I'm just going to put one hydrogen out there. Obviously, you know there's 6, right? And I react it with something like E+. Of course, you have to have a counterion. Mother Nature gets ticked off if you don't have charges balanced, right? So we don't care what the electrophile is. We're just going to call it E+. And I know that that's going to go to give HA plus the carbon electrophile bond. How does that happen? What's the mechanism for that to happen? That's the balanced equation, but that's not the mechanism. It will, but right now let's just assume they're charge separated. The pi bond attacks the electrophile. Why do you say the pi bond attacks the electrophile? You're not wrong. I want to know why you said it, though. Okay, yeah. Pi bonds can behave as Lewis what? Lewis bases. What's an electrophile by definition? It's a Lewis acid. It's nothing more than a Lewis acid, Lewis base reaction. The pi bond reacts with the electrophile. I didn't mess with that double bond. I didn't mess with that double bond. What do I have to put somewhere? I have to put a plus, and where am I going to put it? This card. Yep. I'm just going to put my A- out there for balancing, right? What happened? Am I higher in energy or lower in energy than where I started? I'm higher in energy, right? So I went from a stable aromatic system to now a resonance delocalized carbocation, but it isn't aromatic anymore, right? But it would like to be aromatic again. Tax what? If I do that, then I've added something across the carbon-carbon double bond. Ah, this is still a base, right? So it just simply comes along and abstracts the hydrogen. These electrons come in to form the new pi bond, and we have now made that's about as easy a mechanism as I've taught you all. Pretty straightforward. And it doesn't matter what the electrophile is. This is always how it happens. That's cool. You don't have a whole bunch of stuff to remember, right? You just have to know how to generate the electrophile. Well, if I want Cl+, I need chlorine and iron trichloride. If I want NO2+, I need nitric acid and sulfuric acid. If I want to generate a carbon plus, I need to generate a carbocation. I can do that through an alkyl halide and aluminum trichloride. If I want to add an psyllium ion, make a ketone, I need an acid chloride and aluminum trichloride, right? That's the general reaction. This isn't the tough stuff. The tough stuff is remembering how you get the electrophile. Okay? I know you all can memorize those 3 steps. Okay? What would the energy diagram look like? So here's my starting, here's my product. What would it look like? How? So we come up here to a transition state and go down to what? Just like that?
No. There's another little curve thing.
There's another little curve thing? Something like that, right? What's there? That's where that carbocation is, right? This is the transition state here. This is an intermediate, right? It goes through another transition state here where this is being abstracted, and then we finally get to the product. TS1, TS2, and there's that carbocation sitting right there. Okay? That's what the energy diagram would look like for that molecule, right? And there we've got it. But you all figured it out without looking at it because you saw what the reaction was, right? What else does that reaction diagram look like? What similar reaction does it look to like that we've talked about before? It kind of looks like an SN1 reaction, doesn't it? Does this kind of look like an SN1 reaction? In a lot of respects it does, right? Except we don't have anything leaving at the first step to generate a carbocation. But the overall reaction energy diagram looks identical to me. Easy to remember, okay? So we've talked about the ability of putting the halogens on. Iron trichloride if we want to put the chlorine on and make chlorobenzene. Iron tribromide if we want to put on a bromine and make bromobenzene. I will say, however, that sometimes you will just find them writing, let's take like bromination. They'll write Br2 and then just iron. And it turns out iron tribromide is, it's not that expensive, but it's a lot more expensive than going to Lowe's and buying a bunch of iron nails, okay? And you can literally take a piece of iron nail, put in the reaction, and this will work. Can anybody tell me why? What happens when bromine comes into contact with iron? What do you think it generates? Iron tribromide. It will react with the iron and make the iron tribromide in what we call in situ, without us isolating it. It makes it first, and then it will go on and do the chemistry that it wants to do. So on my exam, you might see me write bromine/iron, and you need to know that that's the same as iron and or bromine and iron tribromide. The same can also happen with chlorination. So I am going to stop there. We're not going to go into the general mechanism of how we generate those electrophiles, so that will not be on the exam on Friday. We have a review on Wednesday during class, right? You all know that I like to do an outside review. I can do one or two. I can either do one, we can do one Thursday evening, and or we can do one Wednesday evening. Huh? Thursday after lab?
Would it be like 6 o'clock or
What time? 6:15? 6:14 and a half, maybe? All right, so Wednesday night? Thursday night? Thursday night. All right. On your way out, you need to turn in your Chapter 12 with your grade on it. Set it up here, and also your note card for your bonus. Please place them on separate piles for me.